The Urison metrization theorem is kind of a climax of this kind of general topology. So purely topological conditions will actually manufacture a metric for you, building on the Urison lemma. So let's me just state the theorem. So in X is a topological space. And the theorem says X is if X is second countable and regular, which implies normal, though we'll just use regular in the proof, then X is metrizable. Okay, proof. Well, the method is, the idea is that we deduce this by embedding X in a product of, I'm going to call this script P for some reason that you'll see, product of 0 ones and indexed by such script P where P is countable. And we saw last video that this product is metrizable. So there's a metric, and we have already seen that the subspace topology on a subset of a metric space is the same as the restricted metric, and so we have this original space is embedded. So the idea of embedding is to use kind of test functions. We'll use functions which are going to be 1 at a point, and then they're going to be 0 in most of the space, and a whole bunch of such functions. And if there are enough of them, then these different points go to different collections of functions. The set of values separate them, and that would mean injectivity, but in a strong enough way that we even have an embedding. And so let us construct these. Of course, we have to use second countability. That's the point. So let's say B be a countable basis. And we'll construct these functions, and as I said, they're kind of bump functions. We're going to look at sets U and V, both of which are basic, but U is sort of deep inside V, which means, so specifically closure of U is contained in V. Okay, and then for these, Urison's lemma will tell you can make it 1 here and 0 here, because the complement of an open set is closed, and it's going to be 1 on the closure of U. So that is, let's look at such sets. For a metric space, you just take a ball and a ball of a strictly larger radius, but we don't have a metric. We are trying to construct a metric. So let B be a countable basis, and let P be the set of all pairs U comma V, where U and V are basic open sets. Okay, so pairs of countable, countable cross countable is countable, so such pairs is still countable, and I pass to a smaller subset, which is where U bar is contained in V. Okay, so by Urison's lemma, for all U comma V contained in P, belongs to P, elements of P, there exists a function FUV, which is going to map our space X to 0, 1, such that F restricted to U bar is 0 and F restricted to V bar is, so I should say hence normal. Well, I said we didn't use normality, but we did use it implicitly. We used Urison's lemma, which uses normality. We saw second countable and regular implies normal, and so Urison's lemma is true. We will also use regular directly, but not normal. So F restricted to U bar is 0 and F restricted to not V bar. That was nonsense. The complement of V instead. Yes, so this is not F restricted to V bar, but F restricted to X minus V is identically 1. So these are disjoint closed sets. So this is a closure. So inside this it's 0, outside this it's 1. Okay, so the key point is so this is the first point, that by Urysohn's lemma we can construct a lot of such functions. But we have to show that this is an embedding. First of all, that it's injective and that it respects the topology. Okay, but now firstly note, so we get an embedding. So we get a map phi mapping x to the product p belongs to script p of 0, 1, which I would write it, in fact, let's as well see, since we know what the set is, it's pairs uv belong to this, where x maps to, well, I have to say what the tuple is. So at uv in p, it's going to be, oh, not x, but a little x, a point in x, will map to the value of the corresponding function at x. Implicitly, we are using sort of double dual construction. That is, a point is a function on functions. So these coordinates are functions. We evaluate it on this. And if we evaluate at a point a continuous function, this is continuous on functions. We have not formally defined what the space of the topology is on the space of functions. Well, we didn't call it space of functions. It's the product topology. So we have these things. Okay, so we want to show that this is an embedding. Okay, so what do we want to show? What we want to show is essentially that, so for phi to be injective, we need fuv of x. We need for all xy in x not equal to y. I'll just write this as a separate statement. We'll prove a stronger statement than this straight away. We need for all xy, if we have 2 points and x is not y, there exists a pair uv in P, that is basic open sets with a closure, such that fuv of x is not fuv of y. So by definition, all the coordinates are the values of these functions. So there must be a function which distinguishes your point x from your point y. Okay, and we'll construct this, and we'll actually construct a little more. So y is so little y is going to be a closed set, and we'll work in greater generality than this. In fact, we'll construct a function which is 0 at y, positive at x, and more generally. So we have the following lemma, and by this which is called, so the way of saying this is FUVs separate points, that would be the previous statement, but from closed sets. Okay, so here is the proof of, so not the proof, but the statement. Yeah, so let A contained in X be closed, and X belong to X minus A, so it's not in A. Then there exists some pair U comma V contained in P such that FUV of X is positive. It will in fact be 1, and FUV of A is 0. Okay, so we just said positive because we want to, that's what separating points from closed sets will mean, and that's all we will use when we in the proof. But in fact, this is done. So the work here is only to construct U and V to be basic. Okay, otherwise, so let's see this. Let's have a picture here. We have X, and then we have A, and we have A. So by regularity, we have a neighborhood U and some set here open disjoint from A. Okay, so we have a neighborhood U, and by passing to a smaller neighborhood, we can assume that U is basic. Okay, so by regularity, there exists a basic open set, and I'm going to call it V because it will be actually that V, such that x belongs to V, and well, instead of saying, so we have W here, its closure is going to be its complement is going to be closed. So saying V is disjoint from this is saying the closure of V is contained in the complement in the closed set, which is the complement of this, and hence is disjoint from A. And so V bar intersection A is empty. Okay. Actually, we don't need this much probably. We'll see later. But we'll in later stages we'll need the equivalent. So this is our set V. Okay. So in particular, X is contained in A is contained in X minus V. The closure part we won't need now, but we will need it at the next stage. Okay, so now how do we construct U? So as U, as V is open, X minus V is closed. So now by regularity, and little x is in a V, by regularity, there exists now U, and again we can take it as basic such that U bar is contained in V. Now we are really using the argument that I mentioned a moment ago, namely regularity tells us that there's a neighborhood of X minus V and a neighborhood of X which are disjoint. We can pass to a smaller one and assume this one is basic, but it's not enough to take V. If I take a neighborhood of X minus V, the open set containing X minus V, the complement of this complement of this, which is the inside of this orange region, is closed. So the closure of U will also be away from V. So the closure of U is going to be contained in away from X minus V. So the closure of U is going to be contained in V. There exists U basic such that this happens, and now it follows immediately. So by construction, FUV equals of X equals 1, and FUV restricted to A is identically 0. So that is what we wanted for separation. Okay, so this has proved injectivity. In fact, it proves continuity. So that's the final step in our proof of Urison metrization theorem. So we haven't stated explicitly criteria for something being an embedding, but it's easy to deduce. So phi is an embedding. That is phi restricted to the image phi of X. And I take its inverse is continuous. So what do we have to show here? This is the space X, and this is a sort of bigger space product of whatever it is, and X is injectively here. What we have to show is that the phi inverse is continuous. That is, given a point here, now point in the image is going to be phi of X. Okay, so that is, given a point which I might as well call phi of X in the image of X. Okay, and now an open set, let me say W in X, containing phi restricted to blah blah inverse of phi of X, but that's just X. So an open set containing X itself. So here we have an open neighborhood which is W. That is, we have continuity just says that there is a smaller neighborhood here, or rather a neighborhood here, U. We have U contained in whatever that is, product of so and so open, such that phi of so that if I look at phi restricted to phi of X, its inverse of U is contained in W. So equivalently, we want to say any point inside here goes to a point. So we want to find U, which is an open set here, so that any point inside here goes here, provided it's in the image. Okay. So this means equivalently, if I take any point Y, so any point here is of the form phi of Y, and its inverse image is Y. So equivalently, phi of Y belongs to U implies that Y belongs to the set W. Okay, so what has this got us? Now W is an open set, and so its complement is closed. Okay, so as X minus W is closed, and X is not, little x is not a point in X minus W, well, we know the FUV is separate points from closed sets. There exists U comma V, a pair, such that FUV of little x is positive and FUV restricted to the set X minus W is identically 0. Okay, so this will let us construct a neighborhood. What we do is we look at the coordinate FUV. Okay, so we take the neighborhood. So we have used. We want to construct U. So U is the product of, let's say, U alpha we are using U and V in this standard fashion. So let me call this something Q, even though it's not conventional for an open set. Anyway, let's take product of Q of UV, where better not to say UV, better to say Q of, so let's take P in script P, QP. Let's look at this product where Q of UV, where UV was this above quantity, is going to be, we'll exclude 0. That is where it is positive, and everywhere else it's going to be the whole space. So the whole space is 0, 1. So 0, 1, where I will have to say this, and QP is all space if P is not UV. Okay, so then if Y, so if phi of Y belongs to U, then what we know is that if we look at the UV coordinate, which is FUV of Y, belongs to 0, 1, that is FUV. So this is an open set, so this is an open neighborhood of Y is positive, which implies that FUV, which implies that, well, we know that on the complement of W, the function is identically 0. So which implies that Y does not belong to X minus W, which implies that Y belongs to W as required. So we just needed a subbasic open set, one particular function, which will separate the complement of W from the given point, and then we see that anything in the product, if we just look at that coordinate and require it to be positive on that coordinate, that will give you only points in the interior of W. Okay, may not all it could be 0 some part of the interior as well. That's not the claim. So U may be strictly inside W, but we just need containment to prove continuity. So this completes the proof of the Urison metrization theorem.